we're going to talk about more of a concept or a definition here because we're moving on to behaviors of graph versus average rate of change. We talk about a graph as increasing as though kind of imagine that you're reading a book from left to right. So I'm reading this graph from left to right. Sometimes it even helps to imagine kind of a tiny man walking along your graph. And so if we have a tiny man walking across our graph from left to right, on that red portion he is climbing up a mountain or a slope. It's not really that steep, but maybe some sort of hill. He's climbing up that hill. So we say that graph is increasing from negative infinity all the way up to 0. And 0 is going to be my bolded line. And I'm saying negative infinity because I have an arrow. So if I didn't have that kind of teensy arrow on the very left side of the graph, I would actually stop. But that arrow tells me from negative infinity all the way up to that point on 0 where that dot is, I'm increasing. And notice how I'm not talking about any of the y values. I'm not saying it's increasing from negative infinity up to 2, because we don't talk about increasing as y values. We only talk about as though we're reading a book, so we talk about the x values. So it's increasing from negative infinity to 0. We say a graph is constant if it's not changing at all. If he's not having to climb a mountain or he's not falling down a slope or anything like that. He just has a nice level playing field. And so that happens on 0 to 2 in the graph. And again, those are my x values. That's my x value interval. So it starts from that red dot and goes all the way to the empty dot on the right side. And it's kind of that blue segment. And now notice how I'm not putting brackets around any of these. That's because the graph, let's look specifically at that red dot point. Well, you could potentially argue that the graph is increasing at that point, and you could potentially argue that it's staying constant at that point. But the truth of the matter is actually neither of those things is happening. There's like a weird point or like a diagonal there that we can't actually determine what's happening. So anytime there is a stark change from either increasing to decreasing or increasing to constant, we're never going to include it. So all of that's a long-winded way of saying anytime you talk about increasing or decreasing functions, there will never be a bracket on your answer. Now for the last part, hopefully you're able to kind of piece together what it's going to be at this point. We want to talk about where our graph is decreasing. And so it's decreasing on that green segment. And we think about decreasing again, if we want to go to kind of that tiny guy idea, is that if he's walking from left to right, he's going to start tumbling down that hill. He's going downwards. And that's going to occur all the way up to infinity because my graph is pointed or has an arrow at the end of it. So I would say my graph is decreasing from 2 to infinity. Now relative maximum and minimum. And I actually would kind of lump this last slide into this concept as well, is these, as far as an idea goes, aren't super difficult. Where it becomes tricky is we have to be careful with the definitions and we have to be careful with how we're describing things. So usually I don't dock points from people's tests about increasing, decreasing just because they don't get the concept. It's that they're not describing the x intervals. They might describe the y intervals, or there's a couple of errors, or like here when we're going through these definitions, sometimes people mix them up or they say, how do I describe this again? So since it's so easy, don't kind of sleep on these concepts. Understand that, yes, it's not that hard to grasp what's going on. It becomes a little bit tricky when you have to explicitly write your answer or explicitly understand what the definition is. So all that's to say is going into minimums or maximums, the definition is very important. So relative maximum. Relative maximum, as far as a strict definition goes, is that the graph starts to go from an increasing graph to a decreasing graph from left to right. And if you're going into calculus at some point, we kind of talk about neighborhoods. It's not that we're talking about really what's the highest point overall in the graph. It's more we're looking at kind of hills or valleys. And what's the top point of each hill? Well, that's going to be your relative maximum. Very similar definition. Your relative minimum is that everything around that, very close to it, is going to be bigger than that point. That's not to say that it's the smallest point on the entirety of the graph, but it's the smallest point in its small neighborhood. Now, Absolute maximum and absolute minimum kind of do fall into that classic definition. Absolute maximum is, I don't really care what's going on at other parts of the graphs. Maybe it squiggles up and down a lot of times. I only want to know the very, very highest point on the graph. And the same thing with minimum, I want the absolute lowest point on the graph. And something to note, relative maxes and relative minimums, I could have 1, I could have 2, I could have 50. There isn't really a set number of how many exist. Where with absolute maximums and absolute minimums, I'm only going to have 1 or possibly none. There is a scenario where I don't have an absolute max or absolute min, and we'll talk about that shortly. So with this graph, we're going to identify any relative absolute maximum or minimum. So we're going to start with, I believe, relative max. Okay, so I do have the answer in front of me, but let's talk through it. Relative maximum for this graph is a negative 216 and 212. So if you're kind of looking at the graph and kind of looking at those points, the negative 216 is the top of the hill on the left side, and the 212 is the top of the hill on the right side of the graph. And so that feels weird. When we think about the term maximum or maxima, we think there can only be a highest point. Get that out of your head. When you see the word relative, you just have to think, okay, where's the top of the hill or where's the bottom of the valley, and kind of look for those in your graph. And those are both described as points. Those are not intervals. So I don't have a relative maximum on an interval from negative 2 to 16. No, I just have that point. The point negative 216 is a relative maxima, and the point 212 is a relative maxima as well. And that's going to be important. Read carefully when you're doing the WebWorks, because they might just want the Y value. They might just want the 16 or the 12. So watch for that. Be careful what they're asking for. And if your answer is not working as a point, maybe just try entering in the second value. My absolute maximum is the highest point on the graph. So we have those two hills. The top of both of those hills, the biggest of the two of them, is 16. So my absolute maximum is negative 216. And notice how one of the relative maxima is the absolute maximum. That happens a lot. So don't kind of be weirded out being like, I already answered the question before. That's fine. But you're not going to have both of them. I don't want the right hill at this point, because that's not the highest point. It's not the absolutely maximum point of my graph. Now moving on to relative minimum. Well, there's only one in this case. There's only one valley, and it's right at 0, 0. So looking at that graph, I kind of going left to right, I have a big drop, and then I shoot up around 0, and then I continue to drop off at the end. And I have an arrow at the bottom of my graph, so I can't say that's a point, so I can't talk about it as a relative minimum. Also, the point at the very, very left side of the graph, that's a dot. We don't ever talk about endpoints as relative maximum or relative minimum. So really the only thing I'm concerned about is a valley, and it needs to go down and come back up. Otherwise, it doesn't count as a relative minimum. Now, that was a lot of explanation to talk about it, and hopefully some of you that you were able to grasp, or ideally all of it you're able to grasp, because this last explanation might take a few listens to really fully grasp, or shoot me an email if you can't fully get it. Don't feel bad. It's difficult. All that's to say, I'm prepping you for what's coming. We're talking about absolute minimum. Now let's look at the definition. Absolute minimum, the least/lowest point on the graph. Well, I'm looking at my graph, and obviously 0, 0 is not the lowest point on my graph, because when I go to the right, it gets much lower than that. So I can't have an absolute minimum of 0, 0. And the truth be told, the absolute minimum is nothing. There is no absolute minimum of this graph. And the reason behind that is when we're talking about relative minimums and relative maximums, we have to be able to give us a point. I have to say the relative minimum is 0, 0, or the absolute maximum is negative 216. And if there's an arrow going all the way to the bottom, there is no point. And anytime you give me a point, like let's say we play a game and you say, oh, okay, you know what I think the relative minimum is I think the graph stops at -20. So let's say 3, -20. Well, the graph keeps going down below that. So -50 is lower than that. And you know it's less than -50, -500. And we can keep playing that game all day because it keeps decreasing endlessly. So there's actually no point we can point at. So watch for that. When there's an arrow going all the way down, there won't be an absolute minimum. And on the other side of the graph, if there's an arrow going all the way up to the positive, all the way to positive infinity, there would be no absolute maximum. So you're only going to find absolute maximums or minimums if your graph stops at some point, or it has a point that is the highest, or a point that is the lowest. You're never going to have it if the arrow goes all the way in that direction. So watch for that. That's kind of a trick question. So rough definition, a power function is anything that can be written as kx to the p, where kp are real numbers, p we call that the power, k we call it the leading coefficient, and we call x the base. But k is very important. We talk about leading coefficients a lot in this section and throughout the next couple of ones. So what's kind of interesting about power functions is it's not really different every time we draw a graph. What that means is that if I have anything that's an even power, I have this picture of this graph right here. These are 3 different graphs. One of them is red, one of them is blue, one of them is green. Do I label them? No, I don't. One of them is x squared, one of them is x to the 4th, one of them is x to the 6th. So they do look a little bit different, obviously. But something that's worth noting is that they all seem to be doing the same thing when we go all the way to the left of the graph and all the way to the right of the graph. And we can see that again with odd powers. The first odd power that we have is in this graph, just y is equal to x, which looks very different from the other graphs. And then I believe one of them is x cubed, one of them is x to the 5th. And aside from the fact that, yeah, they do look different, especially kind of close to the origin, is that the end, they are going in the same direction. So as I go to the right side of my graph, all of those graphs go up. And as I look towards the left side of my graph, all of those go down. And so that's kind of cool that these follow a pattern. Anything that has an even power will either go all up or all down, and anything that has an odd power will kind of flip sides. So we kind of gather that information in this table. And these are the only 4 cases that we'll see. We'll have even powers where your leading coefficient k is positive, where it's negative, and then we'll have odd powers where it's positive or negative. So in the previous slide, we saw the positive cases. So if an even power is, we have a leading coefficient with an even power that is positive, then we have kind of the classic parabola or graph that looks like that. And so if we talk about end behavior, it's kind of maybe a little overwhelming looking at this table at once. So let's just look at the very top left box that has that x squared graph in it. When we talk about end behavior, we say as x goes to infinity, which means as I go to the right side of my graph. That's a really fancy way of saying as I go to the right side of my graph. So when we look at this, as I move to the right side of my graph, well, my graph goes all the way up, which is, it's going to go forever, all the way up to positive infinity. Now, if I look towards the left side of my graph, the same thing happens. My graph goes up, 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 so it goes all the way to positive infinity. And so that's how we talk about end behavior. And if you go into calculus later, you will see this notation a lot. Is yes, we're talking about as x goes to infinity, what's happening to your graph? Well, as we go to the right side of the graph, what's happening? And as x is going to negative infinity, as x is going to the left side of your graph, what is your graph doing? Is it going up? Is it going down? Is it staying at the same value? So to see that again, I think we go stick in the even powers we do. And so we can see this again on the bottom left graph. Now we're saying, okay, what if I have a graph with an even power with a negative leading coefficient? Well, it's the exact same graph that we saw top left, except for flipped. It's a negative in front. So everything is going down versus going up in this case. So again, as the phrasing goes, as x goes to infinity, f of x goes to, well, in this case, negative infinity, goes all the way down. And as x goes to negative infinity, f of x goes to negative infinity again. Both of them are going down. Moving on to the odd powers. odd power as x goes to infinity, we can see that in this graph, goes to positive infinity. As x goes to negative infinity, f of x goes to negative infinity. And then if we flip the sign, if we make k negative, that flips our graph and we see that as x goes to positive infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to positive infinity. Now this is, again, a little bit weird and a little bit overwhelming with notation, but this is kind of what we're asking when we are writing an answer to end behavior. Yes, it's important to know the concept, and yes, when we get into graphing, the concept is much more important than this notation, but this notation is common. So if I were asked a question that was like, what is the end behavior of this graph? I would always be saying as x goes to infinity, and then I would describe what's happening in my graph. And I would say as x goes to negative infinity, I would describe what's happening with our graph. So it is that kind of what filling in the blanks did when we went through this slide. Now, to kind of see this in practice, I kind of shrunk down the table so I have a little bit of space to look over a question. This question says, describe the end behavior of 2x to the 6. Now, it doesn't really matter exactly what the graph looks like. That's not what the question's asking for. If you have a graphing calculator, great, but I wouldn't even want you to sketch a graph. Instead, I would want you to identify things on your table. Okay, well, 2x to the 6, that's an even power. My k is positive, it's positive 2. And so I can look at my chart and see, okay, as x goes to positive infinity, my graph goes to, well, oh, I guess I went with negative. As x goes to negative infinity, my graph goes to positive infinity. And as x goes to positive infinity, my graph also goes to positive infinity. So this is kind of how we're going to start seeing this applied, is we're going to actually look at a function and then relate it back to where that falls into our chart. See this again. Now we have negative x to the 7th, and it looks like I don't have a leading coefficient, but in this case there is kind of that invisible 1 in front of my x to the 7th. So I have an odd power. I have a negative leading coefficient. It's negative 1. And so I look at my chart, and the chart is the bottom right thing. So now my answer would be as x goes to, what do I start with? As x goes to negative infinity, f of x goes to positive infinity. And as x goes to positive infinity, f of x goes to negative infinity. And you could start either direction. You could say, typically kind of the standard is that we talk about the left side of the graph, then the right side of the graph. You could go right side of the graph, left side of the graph, or as x goes to negative infinity, describe your graph, and as x goes to positive infinity, describe your graph, or you could flip it as x goes to negative infinity like we have written here. Really, the important thing is you're saying what's happening on the left side of the graph. I'm going to describe f of x there. What's happening on the right side of my graph? I'm going to describe my f of x there. Whew. Next thing we're going to talk about is even and odd functions. Now this might feel kind of familiar. It's very similar to the concept of when we have an equation determining if it's symmetric about the origin or symmetric about the y-axis or x-axis. The big difference here, though, is with symmetries, you have to check. You have to check all of them. Maybe it's one of them, maybe it's three of them, maybe it's none of them. With even and odd functions, it's either going to be one of the three possibilities, and these are the three possibilities. A function's even if I can plug in negative x into my function, and it essentially doesn't change my original equation. So I'd plug in negative x, I would simplify, compare it to the original equation. If they match, it's even. If they don't match, there's a chance that they would be odd. So again, first step would be to find f of negative x, simplify. And then what I would do is I would multiply my original function by negative 1. I would get negative f of x. That would get me, if that matches, if those two match, then I have an odd function, and otherwise the function is neither. So as I mentioned, kind of this process is that if we find something's even, we stop and we say it's even. It's not going to be odd, it's not going to be neither. We don't have to go through the process, this full process. But the process is essentially the same every time. It all kind of hinges around f of negative x. So I have these three functions here. I'm going to determine individually if they are even, odd, or neither. Starting with the left one, I plug in negative x into my function. And then I simplify, I get negative 3x. I look back at my original function. Those do not match. So I know that it is not even. So now I continue. My next step in my process is to find negative f of x, which, as I mentioned, is I just multiply it by negative 1. So I take my 3x, multiply it by negative 1, I get negative 3x, and oh, those actually do match. The f of negative x and the negative f of x match, so it is odd. Now, something important to note is that when I get to that negative f of x step, and I see that's negative 3x, I don't look back at my original equation anymore. I look back at my f of negative x, the equation right above it. That's what I'm comparing it to. And so since those last two equations match, we say it's odd and we're good to go. Next question, exact same starting point. I plug in negative x for my f of x. Negative x times a negative x gets me a positive x, so negative x squared is actually x squared. And so my f of negative x is x squared plus 3, which matches my original function, and I can stop it. It's even. I don't have to go through the rest of my process. And my last example, I have 3x squared plus x minus 1. Exact same starting point. I plug in negative x. I simplify, so negative x squared is x squared, kind of what we saw in the last example. My negative x is just going to flip the sign for my second term, and then I have minus 1. I look back at the beginning, it's not the same. It's pretty close, but it's not exactly the same, so I would not say it is even. I boxed it because there's going to be a lot of things going on with this question, so I'll know what to compare to. Next, I take my f of x, I multiply it by negative 1. So I go back to my very original function, my 3x squared plus x minus 1, multiply everything by negative 1. I get negative 3x squared minus x plus 1, which is, again, pretty close to, honestly, both of my f of x and f of negative x. But I'm past that step of it maybe being even. This is not even. So now I take that result, negative f of x, compare it to my f of negative x. So these are the two box functions that I'm comparing. I don't care about my original function anymore. We see that they are not exactly equal, and so it is neither. It is important to note that you do need to simplify your function. So in part B, when you plug in negative x, it might not look like they're the same, but once I go through and simplify, they actually do match up. So make sure that you're simplifying things out as much as possible and then making your comparisons.